In this video, we are going to introduce acid-base reactions and the components of those reactions. Here is an example of an acid-base reaction. So we need to look at the different parts that we have to understand them. On the left-hand side over here, we have what we will call the reactants. There are two reactants here, this HCl species and water. Over on the right-hand side, we have what we will call our products. We have two products listed here, this Cl- species and this H3O+, or the hydronium ion species. Between them, we see we have this arrow representing that some sort of chemical change has happened between the reactants and the products. Well, what is that chemical change that has occurred? So if we look at our pieces, what changes do we see between reactants and products? The first thing that stands out to me is when I look over here, there is a hydrogen bonded to that chlorine. When I look on the product side, that hydrogen is no longer there. So that change is pretty obvious. Additionally, when I look at my water on the reactant side, I see we have two hydrogens and two lone pairs. When I look over at my hydronium species, which is very similar to water, I see we have 1, 2, 3 hydrogens attached and only one lone pair. So it would appear to me that this hydrogen has moved from there to here. And the question is, how did that happen? To understand that, we need to think about the electrons that are doing the bonding in this reaction. And so let's take a second and draw on the electrons on our HCl species. So we have 1, 2, 3, 4, 5, 6. Chlorine has 7 valence electrons. There, it's one of them is being used in that bond to the hydrogen. Hydrogen also has 1 valence electron that's involved in that covalent bond between the H and the Cl. Okay. And then when we look over at the Cl species on the product side, we can count 1, 2, 3, 4, 5, 6, 7, 8 electrons. So it would appear that both of the electrons in the bond on the reactant side here became a lone pair on the chlorine. Well, doesn't the hydrogen need that lone pair? Well, let's think about how that hydrogen became bonded over here on the product side. Let's erase some of this work here. And let's think about where that hydrogen became attached to. This lone pair on the water is available to form a bond with that hydrogen and create this bond that we're seeing here in blue. So when we think about maybe this lone pair, this hydrogen, this lone pair, this electron here, forming a bond with that hydrogen, we can think of them being in that bond right there. So as we can see, some species are responsible for using electrons to form bonds, and other species are responsible for donating the hydrogen. On the next slide, we're going to give these species names. Here we have that same reaction, and we have the definitions or the names of each of these species written down below, and we're going to talk about them one by one. So on the reactant side, our very first reactant, we had the HCl, and we noticed on the previous slide that that was a donor, a proton or a hydrogen donor. That hydrogen was donated from that species over here on the other side. Okay, we call the species that donates a proton an acid. Okay, we also saw that the species received that hydrogen by using its lone pair to form that bond. Okay, the species that is accepting the proton with its lone pair, we refer to as the base, and it is the proton acceptor, and it's the species that has the lone pair that's forming the bond. The acid and the base are always going to be existing on our reactant side, or the left-hand side. On the product side, now we can say, well, the HCl used to be the acid, and now it's just this. It's just this Cl. Right? It's not HCl anymore. It's Cl minus. Well, it used to be the acid, and now we would call that, now that it's done its acid job and donated its proton, we refer to that thing as the conjugate base. It's the species that used to be the acid and now is a base, and it has an extra lone pair. Something we're going to see is that bases have available lone pairs, whether it's the base on the product side or the reactant side or the product side, it has an available lone pair. Finally, let's look at our last species. Well, the thing that used to be the base and then accepted the proton, we refer to that as the conjugate acid. That's the thing that used to have the proton and now used to have the lone pair, and now it has accepted the proton. We refer to that thing as the acid. So what do we see across these two trends? Well, we see that this species became this species. It was an acid. It became a conjugate base. This species was the base. It has the lone pair, and it accepted the hydrogen or the proton, and once it did, we refer to that thing as the conjugate acid. I'm going to erase all of my markings now because I want to show something else here. The proton is living here on the acid. The proton is living here. We call that the conjugate acid. The lone pair is available here. We call that a base. That lone pair is available here. We call that a conjugate base. So the place where the proton is currently living on each side is referred to as the acid or the conjugate acid. The thing that has the lone pair back, we refer to that as the base or the conjugate base. One more piece that might be confusing about this is, why am I interchangeably calling a hydrogen a proton and maybe vice versa? Well, there's a reason for that. So when we look at what a proton really is compared to a hydrogen, we've got to look at that subatomic structure. So a hydrogen, the hydrogen atom, we usually say hydrogen is an atom, and we usually refer to a proton as the positive subatomic particle that lives in the nucleus of the atom, right? And so here is the subatomic particles for the hydrogen atom. Hydrogen has one proton, no neutrons, and has one electron. Well, remember when we were talking about how that species works when it's in a bond? So like here for our HCl species, we talked about how 1, 2, 3, 4, 5, 6, 7, 8, these electrons are going to go and live with the hydrogen when this bond is broken. Well, if this electron is going to live with the chlorine, what's left of that, what subatomic particles are left if that electron, the one electron that hydrogen brought to the bonding party, is going with the chlorine? Well, all that's left is a proton. And so that would be all that's left with this H. That H atom is normally a proton and an electron, but if its electron is going with the chlorine when the bond breaks, all that's left is a proton. So you will see us very commonly in acid-base reactions referring to the hydrogen as a proton because it's not traveling with its electron. It's just the proton, the subatomic particle in the nucleus, that is being moved in that bond.